Hello everyone, this is the 6th lecture on microwave remote sensing. From the previous lecture we had started this microwave remote sensing, and in this lecture we will continue this. So, this is just the basics of microwave remote sensing. How do we measure the backscattered energy? So, I hope you understood these concepts in the previous lecture. I wanted to make sure that you understand this concept. So, here you can see this particular tree is interacting first with this incoming microwave radiation, so that it will reflect first, right, before this house. So, you can see this has already started giving the backscattered signal, then it is going back and it will reach to our sensor, right. So, this is when we have our own source of light, when the sensor is having its own source of light. So, as per the definition, this will be the active microwave remote sensing, whereas in the another scenario where sun is our source of light, which is illuminating this particular target, and the incoming radiation is getting scattered back or reflected in the longer wavelength region, and then we have the sensor where it is reaching, right. So, this is the example of active radar, this is for the passive radiometer, right. So, both the scenarios we have working sensors in both the domain, active as well as passive microwave remote sensing. This was meant to explain the concept of side looking radar system. Here you see this particular aeroplane is having a sensor which is active in microwave domain, right. So, it is illuminating this area and with some angle, right. So, you can see the pulse has reached to this particular target first, so that this will start reflecting back and this backscattered energy will reach to the sensor first, right. In this particular scenario, what are the things we are measuring? We are measuring time and backscattered energy. Right. So, these two things are stored, and with this information, with time, we will be able to mark the presence of the house in its own position, right, because it is appearing before this tower, and in this particular field of view this is coming after the house. The height is different because here we are talking about the side looking radar system, right. So, the distance between the transmitter and reflecting objects can be estimated using measured signal echoes. Measured signal echoes is basically your backscattered energy, right. Since the energy propagates with the velocity of light, the slant range, the SR, to any object can be calculated using this formula. So, here C T divided by 2, C is the speed of light and T is your time, and it is divided by 2, and the factor 2 is used because we are measuring the pulse to travel both the distance to and from the target. And remember, this slant range, the range is used to denote this distance. So, range term is used for the distance, right. So, here I hope you understood this. SR is equal to CT by 2, and T by 2 is basically the time it is taking to travel to and fro from the sensor to the target and then to the sensor, right. Sensor slant range, here you can understand this. So, you have this particular airborne sensor which is available to this particular aircraft. Here this is the horizontal plane, this you can consider as the flight path, and this is the surface, right, this is surface. So, you can draw a tangent here. So, let us say this is the tangent. Now, if you just draw a pendulum from here, it will reach to this particular surface, it will touch to this particular surface. This is vertically beneath this aircraft, right. So, this is called nadir, right. So, this is nadir. Now, since we are talking about the slant range, this particular microwave sensor is looking at the ground with certain angle. So, this is the zenith. So, from here you can measure the angle. So, what we will do, we will put a middle line here, right. So, this is the slant range, right, and this particular point which is available here, basically this will become the center of your image. I hope this is clear. Very simple concept, but very important to understand, right. Now, we will talk about few viewing geometry which is involved in microwave remote sensing, because we have to be very careful, and we should have all the information about the viewing geometry to calibrate and characterize the microwave remote sensing data, right. So, similar to optical system, the platform travel forward in the flight direction A with the nadir B, which is directly beneath the platform. Remember the nadir we have discussed. If you just have a pendulum vertically downward, it will touch the ground somewhere, right. And doesn't matter at what look angle your sensor is active, but this will become your nadir, right. And here you have a center line which is your slant range. So, here what it says, similar to optical system, the platform travel forward in the flight direction A with the nadir B directly beneath the platform. So, here this is the A and this is the B, which is the nadir point, right. And now, this particular sensor is capturing this particular area, right. The microwave beam is transmitted obliquely at right angle to the direction of the flight, illuminating a swath C. This is swath C, which is offset from nadir. Offset means this is having a offset, it is not at the nadir. Range D refers to the across track dimension perpendicular to the flight direction, while azimuth E refers to the along track dimension parallel to the flight direction, right. So, this is E and this is D, right. So, E is along track dimension and D is across track. This is across track, right. Now, we will have some nomenclature which is given to these geometries, and that we should remember if you are willing to work in the microwave remote sensing domain. So, this is very important concept, right. So, let us say when the flight is moving in this direction and this is looking at the ground with some angle from the nadir, nadir will be here, remember. So, the angle which is making with the vertical line, this will be the incident angle, right. And then from the nadir, how much angle it has deviated, that is the look angle, right. So, the look angle is here and incident angle is here, and the depression, it is with respect to the horizontal line drawn along with this flight or with this sensor. So, this is your depression angle. So, it is very simple, depression angle, look angle and then incident angle. Now, we will see these terms in detail. The first one is the depression angle, right. So, you see the angle between the horizontal and a radar ray path. So, this is the depression angle and this is the radar ray path, right. I hope you remember the previous slides. Then you have look angle, you see it is getting highlighted here, be careful with this slide, right. So, you just see it is getting highlighted. So, it is with respect to nadir, the look angle. So, the angle between vertical and a ray path, right. Then the third one is incident angle. So, here if you draw a perpendicular on top of this surface, with respect to that what angle it has made, the beam, right. So, that is incident angle. So, the angle between the radar beam and the ground surfaces, that is called incident angle. Then comes the azimuth. You see here, just notice here, this is azimuth. Then comes the near range. So, the portion of the image swath closest to the nadir tract. Now, this is towards the nadir. This is nadir. So, this is the closest point towards the nadir tract, right. So, this is very close to the nadir, right. So, this is called near range. You see, now this is far range. So, the far range is basically, it is farthest point from the nadir tract, right. Then this is the slant range that we have already seen in the previous slide. So, the radial line of sight distance between the radar and each target on the surface, right. So, that is your slant range. Now comes the beam width. What is the width of the beam that is being used in this particular measurement? Then ground range distance, the true horizontal distance along the ground corresponding to each point measured in slant range, right. So, this is ground range distance. I hope all these nomenclature what we are using in microwave remote sensing is clear to you, right. The same thing has been plotted here for better understanding. Here you can see this is the flight path which is looking at this particular ground. This is the swath width, right, and this is how it is moving. The first measurement was taken, then it has moved to this, then to here, and then now it is here, right. I hope this is clear. So, now with the perpendicular on the ground, the beam, the slant range is making the angle I, which is the incident angle, and from the flight path it is making the angle which is called depression angle, and from the nadir, if this is nadir, then this is called look angle, right, and the altitude at which this spacecraft or aircraft is flying, that is the height of the sensor, right, from the MSL. And here you can see the mid swath, far swath or far range or near range, this is near swath. So, all these nomenclature I hope you must have understood. Now, we will understand the range resolution. The ability of a range to distinguish between two targets in the range direction, that is range resolution. So, here you can see this particular aircraft is illuminating this area, right, with these pulses, right. All these are pulses released at a particular interval and they have a fixed width. The width of the pulses are also fixed, right. So, what is happening here? The distance between first and the second pulse, that is called pulse length, right. So, PL is equal to CT or you can say C tau, right. So, this we are using here. So, now it is interacting with these objects A and B, and if A is near, it is close to the nadir, it will interact first and then it will start releasing this back scattered energy, right. So, the range resolution depends on the length of the pulses. So, here what is the length of the pulse, that is very important. If A minus B, if the distance between A and B is less than PL by 2, this is PL, right, and here this is A minus B, A minus B. So, this distance is less than PL by 2. Why PL by 2? Because again we are using this 2 factor, right. So, if it is less than that, we will not be able to identify these two objects separately in our image, right. But if A minus B or if the distance between A and B is greater than PL by 2, then we will be able to distinguish them in our microwave image. For two different objects, it is necessary that the antenna should receive the separate back scattered signal from both objects. So, here you can see both are giving you separate signals, right. So, in this case we will be able to resolve them into two objects. If they are giving only one signal, right, we will not be able to separate them in our image, or we will not be able to identify them in our image, right. If there is any overlap between the signal, resultant image will be blurred. Now, let us see in a scenario where these two are having the separate signal, right, but somehow they are getting overlapped, right. So, in this case what will happen? Image will be blurred. So, this is not advisable, but we can't do it. All depends upon the pulse length and what is the distance between A and B, right. So, that is very important when we talk about the range resolution. Now, the range resolution and the ground resolution, what are they? So, range resolution you have understood. Now, we will talk about the ground resolution. So, here you see, first understand this figure. This is a microwave sensor which is looking at this particular ground where we have all these objects 1, 2, 3 and 4 objects, right. So, all of them are having separate incoming radiation, right, but depending upon their distance, whether we will be able to identify them in our image or not, that will be decided by the pulse length. So, the pulse length, the PL is equal to C tau or CT, where C is equal to 3 into 10 to the power 8 meter per second, that is the speed of the light, right. The complete object is imaged or distinguishable if the slant separation between the object is greater than CT by 2, right. So, therefore, the RSR, the range resolution, that is CT by 2, and the ground resolution RGR, that is CT by 2 cos beta, right. So, here this is very important to identify what ground resolution my data has or my sensor has, or what range resolution it has, right. Now, you see this particular image where the object is here. So, in this case we have considered a bigger object, and here is your sensor, and which is illuminating this particular target with this beam. So, this is your depression angle, this is your look angle. If you draw here a vertical line, that will be your incident angle, right. So, the slant range resolution does not change with the distance from the aircraft, but ground resolution or the ground range resolution does, right, because slant range resolution does not change, does not matter what is the distance from the target and the aircraft, but the ground range resolution will be changed, right. I hope this is clear. Ground range resolution becomes smaller with the increase in slant range resolution. When the depression angle effect is considered, the ground resolution in the range direction RR can be estimated using this formula, right, where T is the pulse duration. This is very important, right. Now, we will understand the azimuth resolution. What is azimuth? Because we have seen the azimuth, right, but what is the azimuth resolution? So, here you can see that this is RA is equal to R into beta, where beta is the azimuth beam width, and here beta is basically wavelength divided by L. L is the length of the antenna. So, now we can modify this equation, and here RA is equal to R into wavelength divided by length of the antenna, and R is equal to H by cos theta 1, right. Now, what is cos theta 1? So, in this equation cos theta 1 is here, right. So, this is theta 1 and H is here, this is H, right. So, estimate RA value when H is equal to 16 kilometer. So, you can practice this, you can try to solve this numerical. Estimate RA value when H is equal to 16 kilometer the height of this is 16 kilometer, right. Theta 1 is 25 degree, this is basically 25 degree, and lambda is 5.66 centimeter. This lambda is 5.66 centimeter and L is your 15 meter. The length of the antenna is 15 meter, right. So, then you calculate the RA value. So, this you need to solve, right. So, this is one example how we utilize this concept to calculate the range azimuth, right. Now, we will learn about the synthetic aperture radar. So, radar antenna can be synthesized electronically into a longer synthetic length. I explained this in the previous slides that we have SAR, which is synthetic aperture radar, where the antenna length is not the real, it is synthesized electronically to a longer length, right. So, that helps us to keep our payloads lighter, right, and that has other benefits also. Synthetic aperture radar, which can be airborne or spaceborne, could collect data over a large distance as it is collected from a physically long antenna, right. So, here considering this is a real aperture radar, so this is let us say 1 meter, but electronically it will be synthesized to let us say 11 meter, 15 meter. So, it has a calculation. So, based on that you can calculate what synthetic length you will have with 1 meter of rear aperture radar, right. This can provide you more information about how do we measure using this synthetic aperture radar. So, here you can see this is the first scene which is getting generated, right. So, this particular airborne microwave sensor, it is looking at this particular ground with this beam width. So, beam width of the real antenna, right. But when it moves to this particular position, it measures this particular area, right. Then when it reaches to this, then it measures this particular area, right. So, here it is illuminating the target, but measurement is happening here, 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 right, and this is called the length of the synthetic aperture. So, this LA is here and this is the flight direction. Now, here you see for this particular target how many images we have or how many times we have measured. So, we had 3 measurement, 1, 2 and 3. From 3 different positions this particular object is getting captured. So, this is the point target. This is one example. Now, with this we will try to understand how the synthetic aperture radar works and then how it is behaving or how it is giving you the information about the target. So, just to make sure that you follow me, this is the flight direction. This is end of the target, this is the first, this is second and third, right. This is the point target and here you can calculate the LA, right, which is length of the synthetic aperture radar. Assuming this is a particular area which has a particular target which needs to be captured in our microwave remote sensing data, right. So, here the synthetic aperture radar, it is available here and this is the nadir. If you draw this, so this will come here, right. So, and this is the ground track. So, this is the flight path and from these 3 locations you are trying to measure this or trying to capture this particular object, right, and this is the swath, right. So, if we talk about the full aperture radar, we have single look. We can have 2 measurements. So, this is 2 look. Then we have 1, 2, 3, 4. So, this is 4 loop. So, this is full aperture, these two are half aperture, right. So, due to multi-loop processing, azimuth resolution reduced by n into LA by 2. So, this is very important. So, due to multi-loop processing, azimuth resolution, refer to the previous slides and then you will be able to correlate them, right. So, this is the example of single look image. You see from one measurement how this particular target, focus on this. Here you see this kind of feature is present. So, keep on watching this particular object. This is with 2, earlier it was single look, this is with 2, right, this is with 4 and this is with 5, right. So, you can see how the image appears when you change the look. This is 10 look, right. So, this is 10 look. Now, you see your target. So, this is just an example how synthetic aperture radar works and how the look improves, or what is your objective, how actually you want to utilize this information in your study. Now, we will talk about this radar equation. So, here the power received can be calculated using power per unit area at target, effective scattering area of the target, spreading loss of re-radiated signal and effective antenna receiving area, right. So, here there are different terms which is explained here. PT is power transmitted towards the target, GT is gain of the antenna in the direction of the target. So, the gain will be provided by the space agency who is launching this particular satellite. R is range distance and sigma is radar cross section or effective scattering area of the target. AR is effective area of the receiving antenna, right. So, these all are used here to calculate the power received by the remote sensing sensor in microwave domain. Further, it is explained the transmitter and receiver both are here. So, the PT is the power transmitted towards the target, GT is the gain of the antenna in the direction of the target, R is the range distance, sigma is the radar cross section or the effective scattering area of the target, and AR is the effective area of the receiving antenna, right. So, and then we are calculating the power received, and based on that it is getting modified, and finally we are using this to calculate the PR, and here the GT is equal to GR is equal to G for a single antenna system. This is important to note. Now, we will see how we can calculate or what is back scattering coefficient, which is very important in microwave remote sensing. So, the back scattering coefficient is defined as the amount of back scatter per unit area. So, we call it sigma naught value. The sigma naught is equal to sigma by A, and it depends upon the target and the system parameter. Now, the roughness, geometry, moisture content, they will be controlling this target parameter, and the wavelength, look angle and the polarization, remember HH, HV, VV or VH, the like polarization or cross polarization. So, those things will be here to define the target and the system parameter, and they will be controlling this sigma naught value. Then it is very important to characterize our data. What is the strength of the signal, whether it has noise, and what is the intensity of the noise in our data. So, that we calculate using the signal to noise ratio, this SNR, and it is very commonly used in different areas, right. So, signal to noise ratio, here we calculate the thermal noise, the PN, the KBT is used, and K is equal to Boltzmann constant, B is the bandwidth, T is the receiver's noise temperature, right. So, here this is used to calculate the signal to noise ratio, and then this PR, if you remember the PR we are using, So, the PR will be referred here. So, in this equation the PR can be calculated using this and Pn will be calculated using this KBT, and K is Boltzmann constant, B is bandwidth and T is the receiver's noise temperature. So, I will continue this microwave remote sensing concept in my next lecture, which is the part 2 of lecture 6. Thank you very much.